Chapter 2.8 is function operations. Now that we know what functions are, we can talk about operations that we can perform on our functions. One thing is we can combine functions using the four main arithmetic operations: adding, subtracting, multiplying, and dividing. So if I wanted to find f plus g, that's simply the function f of x plus the function g of x. If I wanted to do f minus g, I simply do f of x minus g of x. F times g, multiply f of x times g of x. And f over g, you guessed it, f of x divided by g of x. In this case, though, we have to make sure that g of x is not equal to 0. Remember, denominators cannot be 0. So let's take a couple of very basic ones just to start with. Let's say that f of x is x squared minus 1, and maybe g of x 2x plus 1. And we're asked to find f plus g. It's simply the function f plus the function g. So x squared minus 1 plus 2x plus 1, which simplifies to x squared plus 2x. F minus g, same thing, except we would subtract the two functions. But first I would take the function f, and because it's subtraction, I have to be very careful. I cannot just write minus 2x plus 1, because I don't want to just subtract one term from g. I need to subtract the entire function g. In other words, it would be x squared minus 1 minus 2x minus 1, which simplifies to x squared minus 2x minus 2. F times g would be the function f times the function g. Just use your distributive property to multiply that out. We get 2x cubed plus x squared minus 2x minus 1. F over g would be the function f divided by the function g. Okay, and then I always have to check to see if fractions can be simplified, right? But this factors to x plus 1, x minus 1, so no factors in common. Okay, so very basic, very simple, probably exactly what you would do even if you weren't shown how to combine these functions. The domain of combined functions is the intersection of the domain of our two original functions. So if I'm also asked to give the domain of these combined functions, first I have to go find the domain of each of my two original functions. And hopefully we know that the domain of both of these is all real numbers, right? I don't have any of the issues with the domain, like a denominator or a radical. And so the intersection of these, because they're exactly the same, would be all real numbers. That would be the domain of each one of these combined functions. With the exception of this one. Remember, g of x cannot be 0. Denominators cannot be 0. That means x cannot be negative 1/2. So my domain would be negative infinity to negative 1/2, not including negative 1/2, or negative 1/2 to infinity, not including negative 1/2, which is signified by the parenthesis. All right, let's try that again for maybe functions whose domain is not all real numbers. Let's say we have f of x is square root of x plus 1, and maybe g of x is 1 over x minus 2. And I want to find f plus g. Just means take the function f and add the function g. I believe your online homework is going to let you leave it something like this, but really, if I'm going to add these together, I could get a common denominator. To add two fractions, I have to have a common denominator. Once I have the denominator the same, I simply add across the numerators. Okay, same thing for f minus g, except I would have square root of x plus 1, which is f, minus 1 over x minus 2, which is g. Same thing, if I'm actually going to combine them, I would need a common denominator. Whatever you do to the top, got to do the same thing to the bottom. Once the denominator's the same, that's what it is in the answer. F times g is f times g. If I'm multiplying fractions, I multiply straight across the numerator and straight across the denominator. Okay, and let's move down here for our f over g. Again, it is f over g. Now, this gives us a complex fraction, and we cannot leave a complex fraction. So whichever method you prefer for getting rid of a complex fraction, I'm going to multiply the numerator and denominator by x minus 2. So that I can get rid of that denominator, and I have the square root of x plus 1 times x minus 2. Okay, now to find the domain, I need to go up here and find the domain of each one of these individual functions. Remember, if I have a radical, I can't take the square root of negative numbers. So whatever's underneath the radical has to be greater than or equal to 0. In other words, my domain is x has to be greater than or equal to negative 1. Denominators cannot be 0. So x cannot be 2. Now, my domain for all of these combined functions is where these domains intersect. So to start with, I have greater than or equal to -1, but I have to take 2 out of that. So my domain for all of these would be -1 to 2 or 2 to infinity. It's -1 to infinity, but not including 2. Okay, -1 to 2 or 2 to infinity. -1 to 2 or 2 to infinity. With the exception of this one. Remember, I've got to go back and consider the fact when g of x equals 0 and account for that. In this case, g of x cannot equal 0. Remember, what makes a fraction equal 0 is when the numerator is 0. And I don't have a variable in the numerator. So I cannot make g of x equal 0, but I got to be careful of that and account for that if it's possible for g of x to equal 0. But since it's not, my domain is identical to the other 3. So that's combining functions. Another function operation is something called the difference quotient. This is the difference quotient. You don't have to memorize what the difference quotient is, but you've got to be able to use it. The difference quotient is really important. As a matter of fact, when you move into calculus, they'll explain to you what the difference quotient means, and you'll use it over and over and over and over, and they will not wait for you to learn how to evaluate it. That's just the algebra behind it. So it's really important when you get out of a college algebra class that you can evaluate the difference quotient. So a problem would say something like, find this difference quotient for this function. In other words, you don't have to memorize what the difference quotient is yet. Not in this course anyhow. Okay, so I'm going to find the difference quotient for this function. First of all, I'm going to do it in steps. Let's find f of x plus h. Remember what that notation is. That just means I'm going to take the function f, but everywhere there's an x, I'm going to replace the x with x plus h. So 5 instead of times x plus h minus 1. So f of x plus h is 5x plus 5h minus 1. Okay, so I need to put f of x plus h, which I have right here. So 5x plus 5h minus 1 minus f of x, and here's my f of x. So minus, again, be careful with that subtraction. I have to subtract the entire function, not just the first term. And then it's all over h, not f of h, just h. So there's the difference quotient, right? Here's f of x plus h minus f of x all over h. All I have to do now is just simplify it. So I'm going to distribute that negative. 5x plus 5h minus 1 minus 5x plus 1 all over h. And notice here's a 5x minus 5x. Here's a minus 1 plus 1, which leaves 5h over h. H divided by h leaves 5. The difference quotient when f of x equals 5x minus 1 is 5. All right, let's try it one more time. This time, instead of doing this piece separately, I'm just going to immediately put everything in my difference quotient. Okay, remember what f of x plus h means. I'm going to write this, except instead of x, I'm going to write x plus h. There's f of x plus h. Minus f of x, so minus the entire function f of x, all over h. There it is. I just need to simplify it. So I'm going to multiply this out first and distribute that negative. I'd have 1 plus 2. Remember our shortcut for multiplying this out. Square the first one. Multiply everything together and double it. And square the last one. Minus 1 minus 2x squared all over h. Now I've got to distribute this too. 1 plus 2x squared plus 4xh plus 2h squared minus 1 minus 2x squared all over h. Okay, now again, notice what we have. There's a 1 minus 1. There's a 2x squared minus 2x squared. So I have 4xh plus 2h squared all over h. Hey, all of these have an h in it, so if I factor that h out of the top, I can divide them out and get 4x plus 2h as my difference quotient for this function. Okay, we can also plug one function into another function. This is called the composite function or the composition of f and g. Here's what the notation looks like. And this is not red fog and golf, right? Please don't do that. It's f of g, right? And g of f. F of g, or f of g of x, is simply f of g of x. We've done this before where we have plugged in, we just got finished doing it when we did f of x plus h, right? F of x plus h, where I plugged an expression into my function. So the only difference now is my expression is going to be whatever g is. So if I want to find, let's start with just f of g for this function f and this function g. F of g means I'm going to start with the function f. So I'm starting with f. And everywhere there's an x, when I get to x, I'm going to replace it with the function g. So in this case, I'd have 2. And then instead of x, I'm going to replace x with the function g. Then don't forget to finish your problem. That's f of g. Right? May take a little simplifying if we're going to combine those functions. I need a common denominator, so 8 over x minus 1 minus x minus 1 over x minus 1. Once the denominator's the same, it stays the same, and I just have 8 minus x, and don't forget that's a minus minus 1, so 9 minus x. Okay, that's f of g. G of f means you start with the function g. So I'm going to start with g. But when I get to an x, I'm going to plug in the function f. So I have 4 over, but instead of x, I want to replace it with 2x minus 1. 2x minus 1, finishing out my parts of g. I get 4 over 2x minus 2. Don't forget, I've always got to think about simplifying, so I can factor that 2 out of the denominator for a final answer of 2 over x minus 1. Notice that the order matters. F of g and g of f, two completely different things. Now, if I'm asked to find the domain for my composite functions, I find the domain of my second function and my composite function. I don't ever have to, when I'm finding f of g, figure out what the domain for f is. If I've got to do f of g and g of f, I need the domain of all of them. But unlike the combination of functions where I find the domain for f and g and use the intersection, on the composition of functions, I find the domain of my composite function and the domain of the one that was plugged in other words, the second function, and then find that intersection. So if I'm finding the domain for f of g, I'm going to find the domain for this function down here, which is, let me go back and do it in green. Okay, so the domain for this function is, again, we have a denominator, so that can't be 0. So x cannot equal 1. And the domain for g. Oh, the domain for g in this case happens to be the same thing. X cannot equal 1. So here's the intersection. And it never comes into play that I need the domain for f for this one. Okay, so my final intersection of these two sets, since they're the same thing, this domain just cannot be 1. So negative infinity to 1 or 1 to infinity. If I were asked to find the domain for this function, I find the domain for my combined function and the domain for the one that was plugged in, the second one, the f. This is all real numbers. So then I find the intersection between these two, which is the fact that x cannot equal 1. It's just a coincidence that these domains wound up being the same thing, right? The functions are not the same thing, and the domains are more than likely not the same thing. Just a coincidence here. To find the domain for composite functions, you find the domain of your composite function and then intersect it with the domain of the second function, the one that was plugged in to the first function. Okay, I believe that covers it.